Okay, so last time, who can remind me where we kind of left off? Yes.
We were talking about iterative errors.
Yeah.
Supposing that we had like a 3x3 system and then we started calculating, we were debating when we should say this is the tolerance.
Yeah, or when to stop, because the number of the example we showed last time was, and I'll jump a little bit here. So we took this example, this example, and we said, well, beyond what 30 iterations, the answers don't change much. Yet we kept on iterating, and that's inefficient. Okay, so we need a better way to tell the solver. We need a way to tell the solver to stop iterating rather than giving the solver a maximum number of iterations. Okay, so in this example, we gave the solver, hey, do 100 iterations. Well, what if your system doesn't settle down with 100 iterations? What if you need 1,000 iterations? So how could you tell, right? How could you tell how many iterations you need? So obviously, the number of iterations is typically a bad idea to give to a solver. So we needed a sense of an error. And the first error that we thought about was the observation that, so the first observation was that these numbers do not change much. So if we take the difference between these numbers and notice there's not much change going on, then we declare that, okay, that's the best our solver can do. We're going to stop. There's no point in iterating. Okay, there's no point. The solver is no longer giving us any significant digits anymore. But we are faced with a problem when we do this, because if you calculate that error, you still have one error per solution variable. So in this case, we had 3 errors. If in a problem where you have 100 solution points or 1,000, you're going to have 1,000 errors, right? So which error do you pick? And we had different solutions, different answers. Someone said, pick the largest error, the worst case. Someone said, take an average. And those are all legitimate. And then we formalized that idea by introducing vector norms. And if you think of the error for a given iteration, we calculate the error. Just like we said, let's say difference between current iteration and previous iteration. We can make it a relative error. So current iteration minus previous iteration over current iteration, doesn't matter. But that gives you a vector of errors. Now, to calculate an average error or a sense of what the error is, we introduce the idea of vector norms. We introduced 3 norms, the L1 norm, L2 norm, and L infinity norms defined as such. The L2 norm is similar to the Pythagorean theorem, except it applies for an n-dimensional vector. And that vector is still the array of errors, okay? You can choose whichever one you want, as long as you're clear about it. It doesn't matter, okay? And just apply that idea to the vector of errors. In this case, for example, I'm taking the L2 norm. You take these 3 errors. You take the L2 norm, and you get 1 value. And then you could say, is this value greater than my desired tolerance? If it is, then continue iterating until it is less than the desired tolerance. OK. Now, again, which norm do you choose? It doesn't matter, as long as you are clear about it. I typically take the L2 norm. It's just easy and gives you a sense of an average. But they're all good. Typically, the difference would be, yes, L2 norm. Yeah, so these norms, they're called L1, L2, and L infinity. There's L3, L4, L5, and an infinite number of norms. But the ones we typically use are L1, L2, and L infinity. The L infinity norm, you just pick the maximum value in the vector. So you have a vector of errors, and you notice one solution variable is having a hard time converging, or the error in that solution variable is always the largest. So all you're saying is that don't stop iterating until the worst error is below the tolerance. Now, all the other errors could be 0, but you got to keep iterating. OK, so that's the vector norm. The vector norm addresses how we combine this list of errors, this vector of errors, how we combine those errors into one value. And then we say, if this value is below a tolerance, we stop. But what about other error measures? So far, the only error measure we've seen is taking the difference between the current iteration and the previous iteration. Okay? But are there other error measures that we can use? So the one we used is essentially the true approximate error, right? It's not relative because current iteration minus previous iteration, correct? Now, you can divide that by the current iteration, the value of the current iteration. That gives you a relative approximate error. However, the issue there is, what if your current iteration is 0? The value of your solution is 0. Relative error is not defined in that case. Okay? So I tend to avoid that. Okay? I would use the true approximate error, it's not relative. Okay? But are there other errors or error measures? Yes. And as I mentioned very briefly last time before we left class, when you think of a system of equations, AX equal B, okay, or just a matrix, remember that's coming from a system of equations, okay? And as you iterate, your solution, your current iteration vector, substituted in the it's not going to equal to B. It's not going to be equal to B unless you're converged, right? Because you know B, you know A, and you're iterating over X to refine the solution for X. But that in and of itself gives you a definition of another error. If we take our kth iteration, that's the vector of X, okay, of the solution, and we multiply it by A, so AX, if it's equal to B, then, we solve the system. If it's not, then the difference is an error, correct? So we set out to solve AX equal B. We want to solve X from AX equal B. Now, we have values for X as we iterate. So all we do is we take those values and plug them into this system and then ask, are they equal to B? So in other words, another definition of the error, another error we can measure is the difference between the AX of the current iteration and B. Isn't that an error? And as we approach the solution, AX should be equal to B. So, we drive the tolerance down. So that's the equivalent of the absolute error as we defined it in the past. So notice that I defined an error epsilon equal the norm. Now that's a norm, right? AX minus B or B minus AX is a vector. Agreed? Because B is a vector, A is a matrix, X is a vector, but AX is a vector. So B minus AX is a vector of errors. Exactly like we saw earlier. It's a vector of errors. So we need to take the norm of that vector. And that's why you see the notation, these two vertical lines. But notice the notation xk, because I'm taking the kth iteration, okay? Iteration 1, plug in, do B minus AX of this iteration, and, that gives you a sense of an error. Agreed? Do you see this? It's kind of very obvious because we sort of have the answer. We sort of have an idea of what the true answer should be. Correct? Okay. So as long as you do the norm, and that's really easy to implement in Python because AXK is just simply a vector, a matrix vector product. And you already have A, you already have B, so calculating that is really easy. Now, what if you have an exact solution? If you have an exact solution, remember we said, if you know the true solution, you don't need to evaluate an error. It doesn't make sense, right? However, as you develop numerical methods, you want to test your numerical method against systems that you know the answer to, okay? So in that case, you know the exact solution. So another definition of the error is simply x, that should be correct. It should be x to the k minus, so xk minus x exact. Let me correct that. Takes me a second. Okay. So that second error is xk, the current iteration, minus the true solution. Okay? Completely legitimate, right? Another one, which is the one we just looked at, is the difference between the current iteration and the previous iteration. or the solution of the current iteration minus the solution of the previous iteration. Excuse me. Programmatically, that is going to require you to store the previous iteration. So there's the cost of storing the previous iteration and keeping that in memory. Okay? That's the only price you pay with this error. Okay? So all of these are sort of absolute errors or true errors. Yes?
So is it kind of like the previous definition we were using for the error is kind of like the first derivative is how fast we're approaching the real value, and this is like the second derivative, how much that rate we're approaching it is supposed to be?
Not necessarily, because, well, sort of. I can see what you're saying, but if you think of if a solution curve as you approach to the solution, you are sort of looking at that, as you asymptotically approach the solution. Eventually, you want that difference to be 0. So in other words, your slope is going to your curve is going to get flat. But you don't need to go that far thinking about this. Just the way to think about this numerically is to say, is my computer, given the algebra and the precision available in the computer, sometimes you are limited by the precision that the computer can handle. Sometimes the computer can no longer do any better. So if you do an 8-bit, if you do an iterative solver with an 8-bit register, you can only do so many iterations before you hit the limits of what the computer can handle, because it can no longer deal with more significant digits. Okay? So think of it this way. How far can the computer take me in my iteration? How many significant digits can it add? Yes?
So I'm kind of confused how, wait, so are those two bottom equations equivalent to each other?
No.
Okay.
No. This one takes the difference between the current iteration and the previous iteration. Essentially, it answers the question, am I improving my answer? If I'm not improving my answer, what's the point of iterating? Let's just stop. Okay? The other one says, if I have an exact solution, for every iteration, compare that to the exact solution. The first one is saying, how far am I from solving the full system, ax equal b? Okay? Yeah?
So the top one, it's like going towards 0, right?
It should, yes. I mean, they all should go towards 0, right? They all should go to, or a tolerance. So we can never, we can't get to 0 direct. Now, you can also define relative errors. The problem with the first one is it's really hard to understand what ax equal b means. Get a sense of scale of that system compared, for example, to this one. So let's say we do the problem of the heat transfer in a rod. That's going to be on your homework, okay? If you use the first error measure and you're dealing with temperatures within the range of 300 kelvins and kelvins, what is the scale of the tolerance? When you say a tolerance of 0.1, what does that mean? I honestly don't know. But if I tell you I want a tolerance of 0.1 over here, this would be t at iteration k minus t at iteration k minus 1. This is telling me that I'm willing to tolerate an error of 0.1 Kelvin in that difference. Make sense? So if you're dealing with a system where you're in the sun, you're doing like 5,000 and 15,000 degrees, I can tolerate an error of 100 degrees, right? But a tolerance of 100 on the system above, like, I don't know what that means, ax equal b, right? So pros and cons of each error. In the end, it really doesn't matter which one you pick as long as you're clear about it, okay? The challenge would be, how do you choose your tolerance? I really like xk minus 1. That's the one I typically choose. You can do relative errors as well. And again, this one is problematic for 2 reasons. You still don't have a sense of what this means. You're essentially taking the first one and dividing it by the right-hand side. But also, what if the right-hand side has a 0 in the denominator? And same thing here for this relative error between iterations. What if there's a 0 down there? It's going to cause problems in your evaluating of the norm, okay? So typically, I go between either this one or the first one. Again, these are norms because these are vectors. This is the entire solution vector. Okay? Okay. And then, the way you judge convergence, you say, we're going to keep iterating until one of these errors is below a user-specified tolerance. Okay? And when writing an iterative solver, again, it doesn't matter which one you choose, which error measure you choose, with which tolerance, which error measure and which norm you choose, as long as you're clear about it to the user. So that when the user supplies a tolerance, okay, they have an idea of what they're expecting, what their tolerance means, okay? So next, I'm going to post, remember the Jacobi algorithm had two incarnations, the kind of doubly nested loop where you loop over, you do the iteration loop, and then you do the loop over the equations, and then the straight vector shot. And I'm going to share with you codes for both of these. Feel free to use those. Just copy and paste from the PDF and just use them in the homework. But try them first, okay? Try them out first. Okay, so the first one, I'm not going to go through the code. It just essentially becomes mundane here. We can maybe, if you guys are having problems with those, we can sit together and do those. But this is similar to the first incarnation of the Jacobi algorithm where we use the maximum number of iterations to stop. Remember, we had here for iteration less than maximum iterations, right? Now we have a better way of stopping the iterative solver, and that's by saying as long as norm of my error is greater than tolerance, keep iterating. Now notice how I defined my error. I call it R. Why do I call my error R? Because it's a residual error. So in the common lingo of iterative solvers, many people call this residual error. Okay, and that comes from the nomenclature of R equal AX minus B, the residual between your current solution and the true solution. That's an error. You can call it E, whatever you want. It doesn't matter. But I call it R. Now, notice how I define R. In this case, I'm taking the first of the absolute errors, B minus AX, okay? And that's how I'm doing the dot product here, or you can use the at symbol. But you can use the dot product here. I don't know why I mixed those. Anyway, so first I define my initial residual based on the guess, right? Or I could choose a very large value for the residual. But remember, this is a vector, so all of these are vectors. And then you come through the iterative loop, you update your guesses, and then you compute a new residual error by taking B, which is fixed, minus X. And X, you just computed X over there. Okay? And then continue as usual. Now, yes, there's one more step I forgot. So R is a vector. We still need to take the norm of that R. And I showed you just early on how to take the norm in Python. You just essentially call norm from NumPy linear algebra, which is imported up there. From NumPy linear algebra, import norm. And I take the norm of R, and I'm taking the L infinity norm. So essentially, I'm saying the maximum error. Okay? Pick the maximum error and hold your solver accountable to that. Okay? Take it in, copy it. You know, you'll have a chance to play around with it in your homework. But this should just run right out the box. Yes?
Real quick, the at symbol is another way to call it
dot product, yes, yes. It's one of the many perks of Python. They have 1,000 ways of doing the same thing. It's just, and then you build your entire life on one symbol, and then they deprecate it, and then you have to redo it. Anyway, okay. The other version, don't use this one because we're gonna go ahead and you're probably gonna just go ahead and modify this one because the other version doesn't apply to subsequent solvers we're gonna talk about. So don't worry about this one. If you're programmatically inclined, go ahead and look at this and see. It shortens the implementation quite a bit. But if I were you, I would just stick to the first iteration thing. Okay. Okay. Questions? Yes.
I was just wondering, would there be any downside to having like import numpy as NP inside function, like in case you wanted
To make sure that it's there. No, as long as you don't import everything from. So import numpy as NP is a declaration. It doesn't import really anything. It imports it as a symbol. It just imports the symbol, says it's there. But if you do from numpy import star, that's costly. Okay. But I sometimes do it within functions. So maybe you're thinking, hey, I'm gonna put these algorithms, the Jacobi, Gauss-Seidel, SOR, into one file, and I'm gonna call that file, call the functions from that file. Do import in that file. Okay. So, all right. Any questions about his question? Pardon me? Yeah. Oh, bless you. Yes. that was a statement, it wasn't a question. Okay. All right. We can all say bless you to Emily.
3, 2, 1.
Bless you. Okay. All right. Let's go ahead and go to our next iterative solver. And it's called the Gauss-Seidel iterative solver. And one observation to make, let me fix the animation here 1 second. Otherwise, it won't be dramatic. Okay. Okay. 1 second. Okay. Okay. So one observation of the Jacobi iteration is that if you remember the algorithm, we're saying xk plus 1 is equal, everything is xk on the right-hand side. So think about it in the following manner. You go over x1, you say x1 k plus 1 is equal to everything on the right-hand side at k. Now you go to x2, you're saying x2 at k plus 1 is equal to everything at k, including x1 at k. But you just computed x1. You have a new value for x1. So one could say, why don't we use the most recent value? Why keep using the old values? Why don't we use the most recent update? Makes sense? So x1, k plus 1 is going to be a function of all the other x's on the right-hand side. Okay? So you compute that, and then you go to x2. x2 is also going to be a function of all the other x's, including x1 specifically. But in the Jacobi algorithm, we say that x1 needs to be at k, at level k. So let me show you the algorithm again. Okay. Notice xk plus 1 is x at k plus everything at k. Everything is old. So again, go x1, everything xk. x2, everything at k. But we just computed a new value for x1. Why don't we use that value? Right? There's no reason not to. It's an updated value. It's a newer value. It's a better approximation. That's what Gauss-Seidel is. It essentially says, don't use a previous value. Just use whatever is available. Whatever most recent values are available. And just with that, okay, what actually happens for a large class of problems, you will cut your number of iterations by half. So if Jacobi takes 1,000 iterations, Gauss-Seidel will take 500 iterations to get you to the same tolerance. Just by that sleight of hand. Mathematically, what we did, we kept the same formula, except notice I dropped the k over here. And essentially, what that should be replaced with is most recent. So programmatically, what you do, if you go back to the Jacobi code, on the right-hand side, you don't do xguess. You just do xi is equal xi and whatever. Just use just update things in place. Okay? I'm not going to share code with you for the Gauss-Seidel because it's a straightforward update to the Jacobi solver. So over here, notice, we're doing x new, essentially, xk plus 1 is equal x old, and x old over here. all I'm asking you to do with all you do with the Gauss-Seidel is essentially do xi equal xi plus 1 over etc. ai times x. That's it. You just use the most recent values. You don't need to keep track of an old iteration and a new iteration. Just use whatever is available. Okay, that's it. That's another iterative solver. It is much faster than the Jacobi. And that's a summary of the algorithm. Again, remember, notice here I just dropped all the k's. So just update in place. X is literally, programmatically, this is what it looks like. X at I is X at I plus 1 over, et cetera, et cetera. Okay? Just use whatever is available. And I have an example by hand done here, same example we did before. And so remember that same problem. It took us about 50 iterations, I think, to get to a point. To get to a point where we converged. With Gauss-Seidel, within 25 iterations, we converge. So it's about half the cost of Jacobi. Now, for certain types of linear systems, we can prove, actually, that Gauss-Seidel is twice as fast. Okay? Okay, can we go faster? Yes. Okay, how? Well, we can go faster with like Krylov methods and multi-grid methods, but there's no way we can cover those in class, okay? Not even in an advanced course. But I'll show you how to use them in a little bit. But for our intents and purposes, again, the goal here, in real life, when you go out, you're not going to use these solvers. They're actually very inefficient compared to some of the top-notch solvers out there. But they give you an idea of how iterative solvers work. They're simple enough to just comprehend the concepts and get to play around with iterative solvers, get to do some programming, okay? Trust me, this is not a waste of your time. So this is not the mantra, oh, yeah, I learned math, I never used it in real life. You know what? It helps you think, okay? So same thing here, okay? Trust me, this is not a waste of your time. I don't want to waste your time. I don't want to waste my time, okay? So I wouldn't share this info with you if I thought it was useless, okay? Okay, the next leap, and again, sleight of hand, is called successive over-relaxation. That was my English. Okay, today. Anyway, probably because of my eye, but okay, successive over-relaxation. Okay. An iterative method will take us from a solution state, xk, to another solution state, xk plus 1. Okay? It goes like this, right? Now, you can think of this as moving along the direction vector r, defined as xk plus 1 minus xk. And I use r because it's a residual. Okay? But literally, think of this as position. This is an n-dimensional vector, and this is the same another n-dimensional vector. So their difference gives you a sense of direction. Okay? We're moving in that direction. Now, to go from xk to xk plus 1, R is our iterative recipe. It could be Jacobi or Gauss-Seidel, correct? Is our iterative recipe. Is what is the recipe? How do we move in that direction? Okay? Okay? Yes, R is effectively the recipe provided by the iterative method. What is R? It's simply xk plus 1 minus xk, right? So for Jacobi, this would be this R. For Gauss-Seidel, this would be R. Okay? Xk plus 1 minus xk. Okay. So now I'm going to recast this equation by writing xk plus 1 equal to xk plus r. So what I'm saying here is, if I start with a guess xk, to go to xk plus 1, I just need to use a recipe and go along the direction vector r. So that gives you xk plus 1 equal xk plus r. Okay. Here's the great part here. Now, what if we move faster in the direction of r? What if we say, hey, we have an R. Can we scale R somehow to go faster? And then we introduce this nomenclature. We say, OK, xk plus 1 is xk plus some factor, some constant value, times R. What happens? Actually, we will go faster. We will actually go much faster, much, much faster, maybe 100 times faster sometimes, OK? Just by introducing this constant, OK? And this method is called successive over-relaxation, OK? The idea behind it is you're moving along a direction, along a recipe. Remember, R needs to come from a recipe, either Jacobi or Gauss-Seidel. In practice, we use Gauss-Seidel because it is much faster than Jacobi. So think of it as, this R vector as being, shorter or longer, whatever that means. But roughly speaking, the R is the recipe. So pick one of the recipes and multiply it by R, by omega, sorry. Now, why do we call it over-relaxation? Because typically, omega is greater than 1. It's between 1 and 2. But it can be between 0 and 2. If it's less than 1, if you go beyond 2, there's math that shows you will not converge. It doesn't work. But we're not going to worry about that, OK? If it's less than 1, it's under-relaxation. You're moving slower towards the solution. Yes?
How do you determine omega?
Oh, that's a big math question. Okay, for a special class of matrices, like positive, definite, symmetric, there's an actual formula for determining the optimum omega. So, okay, what he's getting to is actually the homework assignment. Part of the assignment is it turns out that there are actually optimum values for omega that will give you the best, the fastest way to get to the solution. But in the vast majority of cases, pardon me, we don't know what omega is. For certain cases, omega is related to what's called the spectral radius of the matrix, which has to do with the eigenvalues of the matrix, et cetera. So I can send you a paper on that. It's it's fun to read, but yeah.
So you can't just pick any value of omega, you have to use a specific value.
No, you can pick any value, but sometimes you may not be lucky to converge. Yeah. Yeah, nope. Now, you can have a intuitive sense of what omega should be if you happen to work with certain types of problems, like the heat transfer problem, these boundary value problems. We know omega should be between 1.6 and 1.75. You get maximum performance out of that. Otherwise, it's just very slow. Now, think about it. The worst case you could do is at omega equal 1. That gives you the Gauss-Seidel. Any value of omega greater than 1, now, and that's going to be in your homework. So take note of that so that you know what your answer is going to be like. Typically, if you plot omega, and if you plot the number of iterations, and if we start omega at 1 over here and omega equal 2, you will see something like this, where omega equal 1 is Gauss-Seidel, right? If you put omega equal 1, you get Gauss-Seidel. And as you approach 2, well, 1.99999, we get to Gauss-Seidel again, okay? But anything in between, it's better than Gauss-Seidel. What we want is this guy, of course. But, it's hard to get. For systems that we are familiar with, you get an intuitive sense of what omega is, and we use that. But again, I never use successive over-relaxation because I use preconditioned full multi-grid solvers, which are like 100 times faster than this one, okay? Okay. You had a question? Got another question?
Yeah, I was going to say, could you iterate it over
Yeah, but then what's the point, right? So that's going to be in your homework. In your homework, I'm going to ask you to take a problem and then plot these curves and show that there is an optimum value for omega, okay? Don't get bogged down in these little details. I mean, this is not the only science out there. There's even more, there's even faster iterative solvers than this. But, I mean, these are important ideas to think about. Started with Jacobi. We knocked down the idea of using the old guess, and that gave us Gauss-Seidel, gave us a factor of 2 speed up, and then we introduced a relaxation factor, okay? Now imagine you can relax each solution entry differently. So imagine omega was a vector, you know, okay. All right, and that's essentially a successive over-relaxation. You take the Gauss-Seidel, and you just simply multiply by omega, this term, 1 over AII. You just put omega over there, okay? All right? Okay, let me see if I can pull up a solver over here. Drive. Google Drive, numerical methods. Okay, so for those listening, so for those who are not in class, we forgot to record all the previous slides. Anyway, we're talking about sparse diagonals, sparse matrices. So scipy.sparse.diags, you give it the list of diagonals. Okay, you could have more than 3 non-zero diagonals. You could have 5, you could have 10. Okay, you give it that list, okay? And then you give it the locations of those diagonals. So over here, the main diagonal is located at 0. So all the locations are, again, with respect to the main diagonal. Main diagonal is located at 0, upper diagonal at 1, lower diagonal at -1. Forget about the format, CSR for compressed row storage. Anyway, this is how you do it. This is how you create a matrix that is sparse. Now, you can operate on this matrix the same way you operate on a standard matrix. If you want to access Aij, you just call Aij. And then SciPy, in the background, it automatically gets to the right entry, okay? There's a little bit, the lookup is a little bit more expensive, ever so slightly, because it needs to go to one array and find the location and then identify what that value is, but that's nothing compared to the cost you're paying by creating these huge dense arrays. Okay, I'll let you have a 5-minute break, and then we will continue talking about sparse solvers in Python, okay? Okay. All right. So sparse storage, that's great. Now, how do we use this sparse storage? Well, we track matrices, etc. Obviously, we want to use those in iterative solvers. One interesting thing you want to play around with is to use the sparse matrices in all the codes we wrote for Jacobi and Gauss-Seidel, etc. You just need to make some adjustments there, because I think the assumption in the codes I gave you was that all of the arrays are NumPy arrays. So certain function calls will not work on those, like shape and length and whatever. So you just have to fix those a little bit if you want to try redoing those with sparse matrices. Okay, so now in real life, you're probably not gonna be implementing SOR. You want to be implementing one of the built-in. You want to be using one of the built-in iterative solvers in Python. Thankfully, SciPy does provide a bunch of cool solvers. And if you go to the SciPy library or just Google SciPy sparse linear algebra, it will land you on this page. Again, there are like 100 pages, and because it's Python, most of them are outdated, but this page is the most recent one I could pick up that has legitimate information in it. Some of the common solvers, we kind of said some names early on when we looked at iterative solvers. Now we're going to say those names again. What they mean, it doesn't matter right now, but you probably want to read up about particular solvers before you use them. If you have a system of equations, a particular matrix structure, you want to make sure some solvers are fine-tuned for certain types of matrices, okay? Like the Thomas algorithm is only fine-tuned for tridiagonal matrices. You cannot use it for a pentadiagonal or like a dense matrix, okay? Similar to iterative solvers. The first solver you could use, which is faster than just the standard NumPy linear algebra solve, is called SPSolve. That's the only direct solver for sparse systems, and it's a very fast direct solver for sparse equations. Remember, we said For sparse systems, we typically prefer iterative solvers, but there are direct solvers that can be efficient. One of them is SPSolve. It's built into SciPy. You can use it. I'll show you how to call it in a second. There's the class of conjugate gradient methods called CG, or BiCG, biconjugate gradient, or BiCG stab, biconjugate gradient stabilized, obviously because the biconjugate gradient was unstable and the conjugate gradient was not enough. So anyway, come up with a bunch of other names there. And then there's the generalized minimal residual methods. There's LGMRAS and MinRAS and a bunch of different names. You can try them out on your systems and just compare those if you're just kind of playing around. Now, probably the fastest solver for transport phenomena is called the algebraic not multigrid. Apparently, this solver is health conscious.
No, it's gonna stay healthy too.
It's gonna stay healthy too, right? Gosh. Well, you know, when you're counting calories, I think I started counting calories a while ago, and like everything I type, there's like multigrain in it. And anyway, just don't eat bread. Okay, probably, okay, well, by the end of the semester, I'm gonna give you a lecture about food, okay? Anyway, okay. Pardon me?
You're actually a nutritionist.
I am a nutritionist by heart. No, well, I grew up, you know, my entire family. We'll talk about that later. Anyway, let's stick with multigrain solvers now. Okay, so one of the fastest solvers for kind of transport type problems is called the algebraic multigrid solver. You know, there's a whole theory behind that. You can just use it. It's the implementation in Python is called PyAMG, which is Python Algebraic Multigrid. And I show you here how you can install it if you want to get it running in your in your notebooks. It's up to you. I'm not gonna require it of you, or if I do, I'll give you exact instructions how to do it. Again, from the SciPy sparse algebra page, you see a list of the solvers they have, and they show you how to use them. You will notice that most of them will require an A matrix, a right-hand side matrix, a guess, a tolerance, and a maximum number of iterations. You can ignore all the other optional arguments, okay? And this is a Python example of doing the system of equations we did for the heat transfer problem. Again, you build these diagonals, and then you do a sparse matrix and build the right-hand side, and it's just call one of the solvers. In this case, I'm calling biconjugate gradient, and that gives you a solution, okay? They all kind of look the same in terms of the interface. Now, let me show you the cost of these solvers, okay? Last year, I put notes that I was gonna, this would be a cool thing to cover this year and also as a homework problem. But I don't think I'm gonna. I changed my mind, okay? So it's not gonna be a homework problem. I'll just show you the results. So us computational people get excited about these things. Okay. All right, so again, I'm solving del squared U equal minus S. Again, think of this as heating a rod. In this case, we're heating a plate because it's 2D. And I'm putting random heating along that plate, just a random number between 0 and 1 on the right-hand side, on an n by n grid. And what I'm going to show is a plot of the time to solution. So we take this, it turns into matrix, and I change the number of points. Again, n by n grid, so you know, start with 16 by 16, then 20 by 20, 32 by 32, and so on. And then look at the time to solve this system of equations. So I'm going to plot time versus number of grid points for a bunch of solvers. And this is what you get. Okay? Whoa, you should say whoa. No, like, yeah. Okay, that was a very good wow. Okay, so starting with this blue line is the direct solver in Python. So that's numpy.linalgebra.solve, A, comma, B. Okay? Couldn't make it beyond like 70 points. And then it just exploded in terms of solution time. Actually, couldn't store the array anymore. Okay? Okay, because the direct solver in Python needs to use the dense array. Okay? Next, okay, I said I'm not going to use the dense matrix. I'm going to use a sparse matrix, but I'm going to do a direct solver. So I use SP-solve. This is what SP-solve gives you. Conjugate gradient gives you this one, but most impressively is the algebraic multigrid. Look at that. Pretty much stays stable across all grid resolutions. This is a 500 by 500 grid. Okay, it's a very big grid, very highly resolved computationally. Okay, very accurate solution. Yet it's a fraction of a second, 0.5 seconds. So it's about what 10 times faster than all the other ones, than the conjugate gradient. Okay, so that gives you an idea of scale and sense of, you know, these solvers matter, but for very large systems they matter. Over here, I could care less, right? Now think of doing this one, this equation, 100 million times. That's not out of the question in the work I do, where I have to do a time-dependent solution, a transient solution, and I take time steps, little time steps, and every time step I have to solve something like this. Okay? I have to solve something like this. And sometimes I have to take 1 million or 10 million time steps to get to the solution. So this, even this fraction of a second will make a difference. Could be a difference between getting to my solution in 1 week or in 2 weeks. Okay? Just to give you a sense. All right, so with that, we'll close the chapter on linear solvers, and we're going to start with another chapter.